Hey guys, what's going on? Welcome back to another low-level learning tutorial. Today we're going to go over AARCH64 or ARM64 assembly, and by the end of this you should be able to write a Hello World program. So let's dive into it. If you haven't already seen my other video on ARM assembly, go ahead and check that out. I'll put it in the description. We go over this slide a little more in depth, but basically we're writing assembly, which is the layer below the high-level language in a form that is not yet understandable by the computer. And then we put that assembly into an assembler that puts it to machine code that the computer can then execute. So like I said before, today we're going to go over AARCH64. AARCH64 is the 64-bit version of the ARM architecture. Because of that, it's still a RISC instruction set, so reduced instruction set compiler, which basically just means that it has fewer instructions than your typical like Intel. And it's a 64-bit architecture, which means that it is 64-bit addressable, meaning it can address a 64-bit wide space. And in this case, the instructions are also 64 bits normally. The biggest change that you'll notice between this and ARM32 is that the registers are now referred to as X0 and X30. So you can actually address the registers two ways. So you can look at them as X0, for example. That will get you the 64-bit register. You can also refer to X0 as W0, which gets the 32-bit lower half of that same register, so right here. And then if I say R0 at all, you can still call the registers R0, R1, R2, and that's just a reference to X0 for that example. The architecture is still byte addressable, which means that you can address a single byte in memory. You don't have to address an entire word, like MIPS, for example. And similarly to how ARM32 had thumb mode and ARM mode, this architecture has 64-bit mode and 32-bit mode. And both of those modes have a user and supervisor mode. Similar to ARM, right? ARM32, 64-bit ARM is the same way. To do an assembly instruction, you have your operator, you have your destination, and you have your source. So for example, to move the value 4 into X0, the instruction is move into X0 the decimal or the hexadecimal value 4, right? Pretty straightforward. And then similar to the previous tutorial, right, to do anything, our process, the user mode area, needs to request a service from the kernel. And the way we do this is using a system call, which in AARCH64 is this instruction. It's service 0 or system service 0. And then when that instruction gets ran, the kernel takes action. The action that it performs, the syscall number, is stored into X8, and X0 through 4 determine how we do it. Very similar to how ARM32 did system calls. So let's pull open our VM here and we go to some of the answers that I have already written. Boom, boom. All right. So here's our VM. We're doing a little bit of work in this. So if you haven't already, go ahead and make sure you install, not sudo wireshark, sudo apt install. It's GCC 7 ARC. So if you type that in, I already have this. You should install this, and then also sudo apt install QEMU. Right. So similar to the previous tutorial, I'm using an Intel architecture VM, but I'm able to test my code using QEMU. QEMU is the emulator suite that allows you to run cross-compiled code in a not cross-compiled environment. It's pretty cool. Cool. So let's write some assembly, right? I think like last time, step 1, we should figure out how to implement the exit system call. Okay, cool. How do we do that? We need to first identify what the system call number is for exit, right? Because exit was system call 1 in ARM32 does not mean it's system call 1 in ARM64, right? That if they change the kernel at all, if they change the binary ABI, right, the way that the binary talks to the kernel, that system call number could change. So we got to look it up in a table. And the way we do that is by, if you go to Google, you type in AARCH64 syscall table. Chromium, just like last time, provides these really good documents on the system call table for ARM64. Cool, so we have ARM64. They are a little different. The more standard like POSIX compliant system calls are handled in the like 64 to 90 range. It's kind of weird, right? So you have like right here, we'll find exit is system call 93 or OX5D. Okay, great. So let's extract this number. So how do we set up a system call, right? So what did I say before? The system call number gets put into X8. So move into X8 the value OX5D. And then what are the arguments to our system call? Well, the error code, right? What it returns, and that goes into X0. Great. So we'll put that into, we'll return OX41. And then how do we invoke the kernel? How do we ask it for help? We say service 0. Boom. So we're going to write that. And just like last time, the way we're going to compile this is we're going to first call the assembler, right? So it's going to be AARCH Linux new AS. We're going to assemble our file, which is 001.asm for me. It could be anything for you guys. And then we're going to output an object file. Cool. No compiler, or no assembler errors, rather. And the object file is the intermediate ELF. It's not executable in its current format because it's not fully compiled into an ELF. It just contains symbol information and code information that we care about. And the way we get it to the final executable format is we invoke GCC on it, and we say we want to compile our object file and output an executable ELF. Okay, we're going to get this error at first, and that's because we're trying to compile it against libc. We don't want to do that, so we say no standard lib. And for the purposes of this tutorial, we're also going to say tax static because there's issues with the AARCH64 build environment on Ubuntu 16. So great, no compiler errors after we add those two flags. And then to test our code, we do QEMU AARCH64 our code. Awesome. And if we did this correctly, we should get the error code 41 or 65 as the output. And we do. Cool. All right, so now that we've written some basic assembly, let's get to that hello world, right? So just like last time, we have to define a label, call it message again, and the message is type ASCII, and it's hello world new line. Awesome, so we've added that, and then we need to set up our system call. We need to add one, right? Because right here we have a exit system call to get us out of the program. Now we need to do a write system call to put data to the screen. So what are the arguments for write? Let's see. So write is system call 64, and it takes argument x0 as fd, so the descriptor we're going to write to. Remember, in Linux we have file descriptors standard in, out, and 0 as 0, 1, and 2. Sorry, standard in, out, error as file descriptors 0, 1, and 2. So fd will be set to 1, the standard out file descriptor that represents the data that goes to the screen. X1 will be a pointer to the buffer we're writing, and X2 will contain the length of that buffer. Great. So let's do that. Move X8, the system call number, which I said was 64. X0 is the file descriptor, so it's going to be 1, which is standard out. X1, okay, so this is where it gets a little different, right? We're dealing with memory operations, so instead of move, we need to load into X1. So we're loading into X1 the address, that's what the equal sign does, of the message label, okay? And then finally move into X2 the length of the thing we're writing. So what is it? It's going to be 5, 10, 11, 12, 13. And then we invoke a system call. Cool, so what are we doing here? We are setting up the system call number, telling it to write to standard out, loading the address of our message into X1, the pointer to our buffer, and setting 13 as the length of our buffer, writing it to the screen, and then getting out of the program safely. All right, let's try it out. assemble, compile, run it. Great. So we've ran our Hello World. Guys, I hope you learned something. If you did, please drop a comment and give me some ideas what you want to learn next time. Thanks for watching. I hope you tune in again. Bye.